Hello friends, this is lecture 2 of Laplace Transformation, and here we're gonna discuss about some properties and theorems of Laplace Transformation and their proof as well. So if you're new to my channel, please subscribe the channel and inspire me to create new contents for you, and also hit the bell icon so you get notified when new video is uploaded. Okay, because each and every video added to this playlist is very important to understand this whole topic, entire topic, Laplace transformation. Okay, so now let us start. The first property we are going to discuss is linear property, that is Laplace transformation of a is a constant here, nothing but it is a constant, function f1 of t plus b, which is another constant, and f2 is another function which is a function of again t. So that's going to be equal to a Laplace transformation of function f1, which is a function of t, plus b, again Laplace transformation of this next function f2, which is a function of again t. So this is the linear property. Now let us prove this property. Now Laplace transformation of a f1 of t plus b f2 of t, and by definition of Laplace transformation, we know that Laplace transformation of a function f of t is given by integration 0 to infinity epsilon e to the power minus st, then f of t dt. That is the result we get according to definition, right? So now if you apply this, now consider this one as this whole thing as f of t, then what we will get. So now let me write it. That's going to be equal to 0 to infinity e to the power minus st into a f1 of t plus b f2 of t dt. That's what we will get, right? So now it can be written as a integration 0 to infinity e to the power minus st f1 of t dt, right? Then plus b 0 to infinity integration 0 to infinity minus s to t, then f of 2 t dt, right? We can write this way. Now again, by definition, this part can be written as a Laplace transformation of f1 of t, then, and this part can be written as b into Laplace transformation of the next function f of 2 f2 of t, which is a function of t, right? That's how we can prove this property. So hope you have understood now. Now let us discuss another property, another rule, that is change of scale property. Okay, change of scale property. Now let me scroll down the page. Now we are going to discuss change of scale property. So according to this property, if Laplace transformation of a function f of t, which is a function of t, is equal to capital F of s, this is another function of s, then by change of scale you can write Laplace transformation of function of at. Here a is a constant, remember that, is equal to 1 by a capital F of s by a. That's what you can write. Okay, so now let us prove this. So first Let us take this left hand side part. Laplace transformation f of a t, and then by definition of Laplace transformation we should get 0 to infinity, then e to the power minus st, then f of t is here f of at. Instead of t we have f of at, then dt, right? That's what we will get. Now let us do one thing. Let us consider at as u, which implies if you differentiate both side by t, then with respect to t, then you will get a du by dt, right? That's what you will get. So we can write dt is equal to sorry, not dt is equal to, yes, dt is equal to du by a, or 1 by a into du, you can write that. So substituting those things here, then what we will get, then Laplace transformation of the function, which is a function of a t, will be equal to 1 by a. So here we have got du by a, isn't it? So instead of dt we will put du by a, and 1 by a will be written outside the integration as it is a constant, 0 to infinity. Hope you have understood this. So now 0 to infinity e to the power minus, so here you see, as we have considered at as u, right? At as u, so t instead of t we can write u by a. Yes, so instead of t we can write u by a, so minus s u by a, you can write that way. Hope you have understood this. Or you can write this way, s by a u, then f of at is considered as u, so we can write f of u, then du. Hope you have understood this. So what we have done basically, so just this t is replaced by u by a, and this dt is replaced by du by a, and at is replaced by u, right? Because at is equal to u we have considered. So hope you have got it. Now what will be the next step in this case? Just what we're going to do in this case, we are going to replace u by t. Let us replace u by t. So if you replaced u by t, then what you will get, Laplace transformation f of at, that's going to be equal to 1 by a integration 0 to infinity e to the power minus s by a this u is replaced by t, then we will get here f of t dt, right? So now what we're going to do in the next step, you can see this s by a, now let us replace this s by a. So let me scroll down the page. Okay, so we are going to replace small s by a by capital S. Okay, then this becomes Laplace transformation of f of at will be equal to 1 by a 0 to infinity e to the power minus capital S t f of t dt, right? Now let me scroll down. By definition of Laplace transformation, this part is nothing but Laplace transformation of f of t, right? So we can write 1 by a is equal to Laplace transformation of f of t, right? And here you see, and here already it is given that Laplace transformation of f of t is f of s, right? So let us replace this Laplace transformation of f of t by f of s, capital F of s. So what we can write, 1 by a is equal to into capital F of s, right? Now as we have replaced small s by a by capital S, so again replace this capital S by s is equal to small a by small s by small a. Okay, replace this, then what you will get, 1 by a dot f by f of small s by small a. So that's what you will get. So that's how you can prove the change of scale properties. Okay, so hope you have understood this. Let me minimize the page so I can show you whole thing in a one font. Okay, so just do one. Yes, so this is the whole thing about change of scale property. So hope you can see it, right? This is change of scale property. Now let us discuss first shifting formula theorem. So now let me scroll down the page, or let me clean this page. And the first shifting theorem says that if Laplace transformation of a function f, which is a function of t, is equal to capital F of small s minus small a, then let me use another ink. Okay, then Laplace transformation of e to the power at and function of t, that's going to be equal to capital F of s minus a, right? This is the first shifting theorem says. So now let us prove this theorem. Okay, so Laplace transformation of e to the power at f of t, which is function of t. So by definition of Laplace transformation, we know the definition of Laplace transformation, that is Laplace transformation of function of t, f of t, that is given by integration 0 to infinity e to the power minus st f of t dt, right? Now let us consider this f of t as this whole thing as f of t. So considering that, using that definition, we will get this is equal to 0 to infinity e to the power minus st, then e to the power at f of t dt. That's what we will get, right? Now here you see from this part, so just okay, now from this part, here e minus st into e to the power at, so that will be e to the power minus st plus at, right? Then take minus t common, then s minus a, or you can write this one as e to the power minus s minus a into t, right? So that's what we're gonna do here. So let me clean this. So then what you will get, integration 0 to infinity e to the power minus s minus a t f of t dt, right? So let us replace this s minus a by r. Okay, just what we're gonna do, let us replace this s minus a by r. Okay, and then what you will get, 0 to infinity e to the power minus rt f of t dt. That's what we will get. So what we have done, replacing s minus a by r, right? So now you see, you can compare this with this definition, right? Now you can compare this thing with the definition. Here we have s and here we have only r. That is the only different. Now you see, by this definition, here you see, when you write Laplace transformation of function of t is equal to integration 0 to infinity e to the power minus st f of t dt, right? And that is given by capital F of s, right? Here you can see, when we used to write here s, we used to write here capital F of s, but we have here r in this result. Here you can see we have r, right? So we can write this one as capital F of r, right? So if you write that, let me clean this. So what we have got finally we have got that Laplace transformation of e to the power at f of t is equal to, so you can write this one as capital F of r. Now as we have replaced this s minus a, here you can see s minus a by r, so that's why again replace the r by s minus a. So you can write this, instead of r you can write again s minus a. Replacing r by s minus a. Okay, so that's how we can prove this first shifting theorem. So now here you can see first shifting theorem is proved, right? Hope you have understood. Now let me scroll down the page. So now second shifting theorem says, if if Laplace transformation of function f, which is a function of t, is equal to capital F, this is function of s, and another function g of t, which is function of t, is equal to such that f of t minus a, if t is greater than a, and it's equal to 0 if t is less than, not less than a, t is greater than 0 and less than a. Okay, then Laplace transformation of g of t is equal to e to the power minus as into capital F of s. So that is the second shifting theorem. There is another form of this theorem, I will show it later. So before that we need to discuss the unit step function before we discuss that form of this theorem. First let us prove this form of the second shifting theorem. Okay, so let us prove this. So proof. So now you see Laplace transformation of the function which is a function of time g of t. So by definition of Laplace transformation, we have 0 to infinity e to the power minus st gt dt, right? That's what we will get by definition. Okay, instead of fe we have gt now, so g of t. Okay, so hope you have understood that difference only. So now here you see this can be written as this can be split into two parts. One is 0 to a, sorry, integration 0 to a, another integration a to infinity, right? We can split it. So 0 to a e to the power minus st g of t dt plus then e to the power minus st then g of t dt, right? That's how we can do. So why we have done here, you can see we have two conditions here. This is g of t is equal to f of t minus a for t is greater than 1, greater than a. Greater than a means from a to infinity, right? From a to infinity, and t is greater than 0 and less than a, so we can consider it as from 0 to a, right? So hope you have understood this. Now let's come to this point here. So here for this condition 0 to a, when t is between 0 and a, for this condition this g of t is 0, right? So this part becomes equal to 0, right? So hope you have understood. And for a to infinity, so for this part a greater than if when t is greater than a, so we have g of t is equal to f of t minus a. So we can replace this g of t by f of t minus a. So we have got 0 plus integration a to infinity e to the power minus st. Instead of g of t, we can write f of t minus a dt, right? So hope you have understood this. Now what we're going to do, let me scroll down the page. So let us put t minus a is equal to u, so which implies if you differentiate dt is equal to du, right? Dt is equal to du. So then what you will get from this part, this is equal to now this, right? Laplace transformation of g of t is equal to, we have got this. So here what we're going to do, here we're going to replace this t minus a by u, right? And if you replace this t minus a by u, then here you see this t can be replaced by t will be equal to u plus a, right? So hope you have understood this. Then what we have got here, so we have got 0 to infinity e to the power minus s. Instead of t, from here we can write u plus a, then f of u du, because dt equal to du, right? So we can write this. That's how we can write. So now here what we are going to do, in this case we had a to infinity here, right? Here it is a to infinity, but I have written here 0 to infinity. Why? Because you see here the function is f of t minus a, right? And here f of u, and here you can see when t is equal to a, if you put t is equal to a, then you will get 0. So that's why here instead of a to infinity we will write 0 to infinity when we will replace this t minus a by u. So hope you have got this. These are basic things of integration. So hope you have understood this. So now what we're gonna do from this part, here you see this part, you can write this one as minus e to the power minus su into minus sa, right? So here the variable is only u, so you can take this part outside the integration. So you will get, let me scroll down the page, you will get e to the power minus sa integration 0 to infinity e to the power minus u, then f of u du, right? That's what you will get. Now simply replace the u by t. Then what you will get, Laplace transformation of z of t is equal to e to the power minus a 0 to infinity e to the power minus st f of t dt, right? And by definition of Laplace transformation, this part is nothing but Laplace transformation of f of t, right? Laplace transformation of f of t, which is equal to capital F of s, right? Which is equal to capital F of s. I have already mentioned here, right? If Laplace transformation f of t is equal to capital F of s, right? It is already mentioned in the theorem. So we can write this as e to the power minus sa capital F of s. That is the second shifting theorem. So hope you have understood this. Now there is another form of second shifting theorem. That is what, let me write here, and that form is, so if Laplace transformation of the function f of t is capital F of s, which is a function of s, then Laplace transformation of function of t minus a into another function u of t minus a is equal to e to the power minus as capital F of s, okay, where u minus ta is equal to 0 when t is less than a, and 1 when t is greater than equal to a, and this is called unit step function, okay? Unit step function. So hope you have understood this. This is called unit step function. This u of t minus a, which is equal to 0 when t is less than a, and it is equal to 1 when t is greater than equal to a, okay? So how to prove this? Now let me show you the proof. Let me scroll down the page. This theorem. So take the left hand side, Laplace transformation of f of t minus a into u t minus a. By definition of Laplace transformation, we know the definition, that is Laplace transformation of f of t is given by 0 to infinity e to the power minus st f of t dt, right? So here this f of t is nothing but this one, this whole thing is f of t, right? So by that definition, what we will get, 0 to infinity e to the power minus st into f of t minus a into u t minus a dt. That's what we will get, right? So here you see t is less than a, we can consider we can split this one into sum of two integrals, isn't it? So here if we apply the laws of integration, simply algebra of integration, then this t less than a, for it we can consider 0 to a, right? And for this part t greater than a, greater than equal to a, so here we can consider a to infinity, right? A to infinity. So that's why we will get that 0 to a e to the power minus st f of t minus a. So here you see this part u of t minus a, for 0 to a, when t is less than a, so its value is 0, right? Its value is 0. So that's why we will write here 0 dt, then plus, then a to infinity e to the power minus st f of t minus a, and for t greater than a, for t greater than a, value of this u of t minus a is 1, so here we will write here 1. Instead of u of t minus a, we are going to write 1 dt. That's what we will get. So 0 into anything is 0, that's why this whole thing becomes 0, right? So what we have got finally, we have got Laplace transformation of f of t minus a into u of t minus a is equal to, we have got a to infinity e to the power minus st f of t minus a dt. That's what we will get. Now what we're going to do, let us put t minus a is equal to u, which gives t is equal to u plus a, and differentiating both sides with respect to t, you will get what 1 is equal to du by dt, which is gonna give you dt is equal to du, right? That's what you will get. So, and one more thing, so here you see we have a to infinity, right? The lower limit is a and upper limit is infinity. So when t is equal to a, right, when t is equal to a, so when this t is equal to a, then a minus a, then u becomes 0. That's why when you will replace this t minus a by u, then this limit will be 0, right? So that's why we can if you substitute these values, that what we have got here, then what you will get, then you can have Laplace transformation of f of t minus a into u of t minus a. On the right hand side you will get 0 to infinity e to the power minus s, t is replaced by u plus a, because t is equal to u plus a, then f of, instead of t minus a we are considering u, then dt is equal to du, right? Dt is equal to du. That's what we have got. So let me scroll down the page. So simply replace this u plus a, don't replace now. So we have one more thing to do, that is what, so here from this term again what we can write, we can write this is into e to the power minus a, right? As this part is constant, it can be taken out outside of the integration. So what we will get, e to the power minus s a integration 0 to infinity e to the power minus s u f of u du, right? Now simply replace the u by t. Okay, so then what you will get? Then you will get e to the power minus s a 0 to infinity e to the power minus s t f of t dt. Just u is replaced by t. Okay, then then what we will get now, by definition of Laplace transformation, this part is nothing but Laplace transformation of f of t, right, which is equal to capital F of s, right? So what we can write, that is why we get we can write that e to the power minus s a is equal into Laplace transformation of f of t, right, and which is given that which is equal to a this is equal to nothing but capital F of s, right? So that is already given here in theorem, that Laplace transformation of f of t is capital F of s. That's what we have used here. Okay, so hope you have understood this. That's how we can prove. This is the another form of second shifting theorem. So in from the next video we are going to solve some problems. Okay, so thank you for today, and if you have understood, then please share with your friends and hit the thumbs up button and inspire me to create more contents for you. So please subscribe the channel if you are new to my channel. Thank you for watching.